Mark, can you hear me still okay?
I can hear you.
Okay.
Can you guys hear the background noise?
No.
Not really.
I have my window open right now.
I cannot hear anything.
Okay.
Okay.
As long as I can keep that window open, I would appreciate keeping that window open as long as possible.
That's fine.
Okay, I think I'm go ahead and start. Okay. Hi everyone. I'd like to welcome everyone to SUNY Brockport Geology Seminar. We have a speaker from Smithsonian Institution today, but before I introduce the speaker, please let me explain how you can ask a question. There should be a Q&A icon to open the Q&A window where you can type. Oh, let me mute it. How's this? Sound better? So there should be a Q&A icon to open the Q&A window where you can type and submit your questions. Then our moderator, Dr. Noel, is going to pick questions or consolidate similar questions and then forward the questions to the speaker. So I cannot guarantee all the questions asked. Nonetheless, we appreciate all questions and please submit your questions as many as you want. Okay. I keep hearing everything twice. How about, yeah, I don't know what's wrong. How's the audio? Mark? Like, is it doubling, echoing?
No, I hear you fine.
I also hear you fine.
Hearing my voice okay?
Yep. One thing too to attendees, if you think of a question during the talk, go ahead and put it in the Q&A section, and I'll see it, and then but we can ask them all at the end.
Okay. So, are you hearing my voice okay or like echoing?
No, you're good.
Okay. So today we are privileged to have a speaker, Dr. Emily Martin from Center for Earth and Planetary Studies, National Air and Space Museum, Smithsonian Institution. The title of her talk is Cracking Through Enceladus Ice Shell with Tectonic Pit Chains. Emily?
Thank you so much. So I'm going to show you a couple more field photos of pit chains in Iceland, as well as more like this that you can see on the right-hand side of your screen that are pit chains from Saturn's moon, Enceladus. So to give you a little bit of background on Enceladus, if you're not familiar with it, Saturn has a lot of moons. Enceladus is one of them. Enceladus is pretty special because it not only forms Saturn's E-ring, which is this really diffuse, I don't know if you can see my cursor, but it's this really diffuse region right here, and that's all material coming out of Enceladus' south pole. Enceladus is really tiny compared to a lot of other moons. But it is a really interesting moon that we've seen mostly through images of Cassini, a mission that just ended in 2017 that was running through the Saturn system. And we care about Enceladus in part because it's what we now call an ocean world. And an ocean world is essentially a place that is covered in a layer of ice, and then there's a liquid water ocean layer before you get to the rocky core of the moon. This is Enceladus here on the left, and you can see these blue cracks. That's the South Pole. Those are cracks called tiger stripes that were revealed by the Cassini mission. And Enceladus is this really bright white, bright place, partly because of the surface being completely mantled by this fresh, think of it as a little bit like snow, coming out of the South Pole. Now this is the South Pole. I've turned it upside down, so just envision you're looking at it from underneath. But all this material. It's mostly water vapor, gas, and ice particles coming out of these tiger stripes or these fractures in the South Pole. And a lot of that material is falling back down onto the surface, which is why Enceladus is so bright and reflective. And Enceladus is really small. It's about the size of Washington State. But what this means is that there's an awful lot of water on Enceladus because we have a water ice.
So it looks like Dr. Martin froze. We'll see what we can do to get her back here in a minute. So just hold on.
Okay, seems like we have technical difficulties. Emily just sent me a text saying that her laptop just crashed and she's rebooting now. Mark, you can sing a song while we are waiting.
Do you want me to share my screen? I had Pink Floyd Dark Side of the Moon on.
I'm really sorry about that. My computer just rebooted itself. It's very annoying. I'm sorry.
That's really quick still.
So I am essentially ready to go into screen share, and
Okay.
I'm ready when you guys are.
We are ready. Once you share your slideshow, I can bring that up.
Super annoyed.
So it's not as bad as when I was giving a quiz a couple weeks ago and a student frantically emailed me, I'm assuming from her phone, saying, my laptop, I just turned my laptop on and it decided to go into update.
Been there too.
Right, so these things happen.
Well, my camera shut off and I was like, well, that's weird. I wonder what happened. And then my screen went black and I was like, oh, my computer has decided to reboot itself without giving me any warning.
Okay, I think we are ready to resume.
Are we ready to resume? Everybody's still there?
They are.
They are.
Yeah, go ahead.
Nobody
Okay.
left.
Well, I'm sorry for that. Sometimes computers just have it in for you, and today is that day for me. So we were talking about Enceladus, which is a tiny little moon of Saturn, which is made out of a lot of water ice. And when Cassini really established that there was this geologic activity in the South Pole and there was all this material falling back down to Enceladus' surface, it really helped establish this class of bodies that we used to call icy satellites because they were made out of water ice, but now we're starting to call ocean worlds because what we're realizing is that there's so much water distributed across the solar system. And of course we care about water because we care about whether or not other planetary bodies in our solar system might be able to host extraterrestrial life, right? Are these habitable environments? Are these places where life could have evolved independently of Earth? And so I really like this diagram because it shows you just how much water there is in the solar system. These blue dots represent how much water, relatively speaking, is inside each one of these bodies. So on Earth, you have this blue little dot. On Pluto, you have so much more water on Pluto than you have on Earth. This is Ganymede, one of Jupiter's moons. Europa is another moon. of Jupiter, and Titan, which is a moon of Saturn also. And you can just see how much water is in our solar system outside of just our Earth. And what that really does is sorry, this is another infographic that I also really like, but we're going to skip ahead because I know we lost a few minutes. So what that means is when you start to think about where there are places in our solar system that could host life, or where life could exist and maybe even evolve, you not only need water, but you need to have the right chemistry, and you need to have an energy source. You also need to have time, right? You need to have water and an energy source and the right chemistry for long enough for life to exist. And so we're thinking about ocean worlds as this new astrobiological frontier. I'm not an astrobiologist, and I'm not going to give you a whole host of information about astrobiology, but what I really want you to start thinking about is sort of moving away from this idea that the rest of the solar system is barren of any kind of life, because this idea of ocean worlds is really starting to give us this sense that we're no longer in what used to be called the Goldilocks zone. What we're in is this region where, you know, rather than having the right temperatures to have liquid water at the surface, which is what defines our Goldilocks zone, right? Sort of this a little bit further out than Venus and a little bit closer in than Mars, which is where Earth is, you can have liquid water at the surface. And since we're realizing that we have liquid water in all these other reservoirs across the solar system, as far out as Pluto or even further, we maybe now need to start thinking about what a habitable zone really is. And this has a lot of implications for exoplanets, which we're not going to get into today, because what I really want to talk about is how holes in rocks in Iceland can help us understand the ocean on Saturn's moon Enceladus, because I think these two things sort of don't seem like they go together. So they go together because of these features called pit chains, which I showed on my title slide. And we find pit chains across the entire solar system. You get them in Earth and Iceland, which I'm going to talk about, but you get them on Mars and Venus, on a lot of small bodies like Phobos and Eros, which is an asteroid, and Vesta, all across the solar system. But they form in different ways, which is why I made a distinction to say that I'm talking about tectonic pit chains today, because you can get pit chains forming as the result of volcanism, karst dissolution, water interacting with carbonate rocks. But we're talking specifically about pit chains that are forming in extension fractures or dilational faults, essentially places where there are cracks that are forming by being opened up rather than being pushed together. And you get the pit because as that crack starts to open, you actually have a layer of material on the surface, loose, unconsolidated material that's actually going to drain into the void space that you create when you open up that crack. And so when you see a pit chain, if it's this kind of pit chain, we think it's a really useful tool because we have the same kind of feature on Enceladus. So we have tectonic pit chains on Enceladus, and they're all over the surface. And we know that they're tectonic in part because of how they look, or their morphology. And we can look at other kinds of pit chains across the solar system. So these are on the moon. They're lava tubes where the roof of the lava tube is actually collapsed, and it creates these collapse features along the length of the lava tube. This is karst dissolution, like I showed you before. You do get these kind of funny shaped pit chains, but that has to do with carbonate rocks, which we're not dealing with on Enceladus. But if you actually compare the dilational faulting pit chains that you see in Iceland to these funny little features you see on Enceladus, and as you can see, they are these chains of isolated individual pits that are really parallel to one another, and they move across the surface. They're indicating that not only do we think they're tectonic, but they're indicating that we think we have a layer of loose, unconsolidated material on the surface. Now, the material, like I said before, it's coming out of the south pole of Enceladus and coming down onto the surface, sort of like fresh snow. And this is really interesting when you combine it with the presence of pit chains, because we know pit chains are actually really very young. And we know that they're young because of the fact that pit chains sort of lay on top of everything else we see on the surface. So over here on the left, you can see we have pit chains indicated by these arrows, and they are cross-cutting. They cut on top of something else, which means they happened more recently than the thing underneath them. And when you map them out, this is a simple cylindrical projection of the surface of Enceladus, you can actually see their distribution is kind of interesting, right? There's these places where the pit chains haven't formed or that we haven't observed them, which is really interesting. But if pit chains on Enceladus mean that there's a layer of regolith or loose unconsolidated material, we might be able to use them as a tool. Now, I want to take a moment to really define what I'm talking about when I say regolith, because if you study the Earth, which a lot of people do, regolith is this layer underneath a soil layer when you look at the Earth. If you study the moon, and you've been studying the moon for a long time, regolith is something that's only generated by impact craters forming on the surface of a planetary body and really breaking up the material on the surface. But another definition of regolith can simply mean loose unconsolidated material, sort of like sand. And so that's really what I'm talking about here, is simply regolith being loose unconsolidated material like the stuff that comes out of the south pole of Enceladus. And this is a cool picture from Cassini showing you all the stuff flying out. So we think that pit chains signal that Enceladus's surface is mantled with a layer of loose unconsolidated material. This is a really amazing image of Enceladus. It's being backlit, so the Saturn's rings are being lit up. You can see its plume being lit up there. And all that material is falling down on the surface. So as Enceladus's surface is getting cracked by all these tectonic features, which are all these skinny little lines that you can see sort of going north and south through here, we're realizing that we have regolith everywhere, and we can use that. As I mentioned, a lot of that regolith is coming out of the South Pole, these plumes, and these plumes are actually being sourced. These plumes are being fed by that liquid water ocean that I was talking about. Enceladus is an ocean world. There's a liquid water ocean underneath its surface. So that ocean is actually coming out of the South Pole. Now, about 90% of that material falls back onto Enceladus's surface. The other 10% doesn't come back to Enceladus directly. It goes out into Saturn's E-ring, which is this really broad, diffuse band of material. And in addition to the E-ring, the material from the plume will go out into the E-ring. The E-ring material will sometimes find its way back onto Enceladus's surface. So that's two sources of material falling onto Enceladus's surface, creating regolith. But we also have impact-generated regolith. Parts of Enceladus's surface are heavily cratered, which means that surface is being bombarded and it's being broken up into smaller bits, which also is part of the regolith we're looking at. So while we're most interested in the regolith that's coming out of the plume, we also have these other sources of regolith that we have to contend with. So the next question comes, we have material coming out of the South Pole, it's landing onto the surface. If we can say how deep that material is, we might be able to say something about how long the plume has been depositing material on the surface. And that tells us something about how long the plume has been erupting, which means that as long as the plume is erupting, we have a layer of liquid water on the inside of Enceladus. If we know at least how long the plume is erupting, we know how long the water has been there, and we know how likely it might be for something to be living inside that ocean. If it's a really young ocean, something wouldn't have had long enough to kind of evolve and create a habitable environment. But if it's been erupting for a really long time, if it's taken a really long time to accumulate all this regolith on the surface of Enceladus, then maybe we're much more likely to have a habitable ocean. So we're really trying to get at this question of how long has the ocean been present by trying to ask the question, how long has the plume been erupting? So we're going to use pit chains as a tool because pit chains are a hole in the ground. We have pictures of these holes in the ground on Enceladus. And so we can use things like the pit diameter, the shadow that the sun casts, right? So there's a shadow inside each pit. We can start to do some really basic geometry to make an assessment of how deep that pit is. And we're going to make the assumption that the depth of that pit is at least as deep as the regolith it's forming in. So the way I've drawn this picture is that the pit actually goes as deep as the layer of regolith. We can't know that, but we know that the regolith has to be as deep, at least, as the the regolith. So on the right-hand side of the screen, you can actually see that this is a really high-resolution image of a single pit on Mars. We don't have this kind of resolution on Enceladus, but this is a really nice example of what we're talking about, where we measure the whole pit's diameter, we measure the length of the shadow, and from there we just do a little bit of math magic and we can calculate out how deep we think that pit should be. And we're using pit depth to represent regolith depth, or I should say minimum regolith depth. But we don't know how well these assumptions hold up, right? Like when you're making measurements on an image collected from a space robot, essentially, we're making a lot of assumptions. And so we want to know, how well does the depth of a pit correlate to the depth of the regolith that it's forming in, right? Like that's a really big assumption we're making, and we want to know how close we are. And so Iceland actually provides a really great opportunity for us to test this. On the left, you can see pit chains on Enceladus, and on the right, we're looking at pit chains in Iceland. So their scales are totally different. If you look at the scale bars, you'll see that the pit chains on Enceladus are much larger than on Iceland. But they look very similar. And so we think that they're a really good analog. We can go and actually look and touch and measure pits on Iceland, and we can compare that really easily to what we're seeing in the images of Enceladus. So we can go and actually figure out if in the field these kinds of geometric relationships hold up, because it's really easy to go ahead and draw these kinds of schematics and just hope that it works. But we have an opportunity to go out and test it. And there's very few opportunities for us to actually go and do field work that's relevant to what we're seeing on icy satellites, right? Field work in Iceland and Hawaii are really great analogs for places like the moon and Mars. So there's a really not a lot of opportunities for us to do these kinds of studies. So we spent 2 field seasons in northern Iceland in right around this black box. And if you're familiar with Iceland at all, this red triangle represents the Krafla volcano. And then on the right-hand side of your screen, you can see that we had 3 different field sites that we explored. And what's really interesting about these 3 different field sites is they have 2 really different materials. So sites 1 and 3, you can see, are both really pretty green, which means they have a lot of this really dense sort of low-lying shrubbery, which has a lot to do with kind of keeping the soil sort of in place. Site 2 is really interesting because it's pretty close to the coastline. And why that's important is that there's this huge delta area. And so all this sort of dark material that you're seeing is actually this kind of loose granular material. It's essentially basaltic sand. It's like black sand. So you can see at field sites 1 and 3, the only reason they're different is we were there at different times of the year slightly. So in field site 3, it's very brown because we were there later in the year. Site 1 is very green because we were there earlier in the year. But what I really want you to notice is that in site 2, that looks like a sand pit, right? Like it's this very sandy material. And we think that that really has a strong effect on whether or not there's a relationship between the pit depth and the material it's forming into. So if you remember back to that schematic diagram I showed you, we're assuming that a pit is what we're calling a right cone, right? It's essentially a cone, and at the bottom of the cone it's about 90 degrees. So we first make the assumption that it's more of a cone shape than a bowl shape. So we did some really basic digital elevation models. I did this with, I'm not kidding, it was like a 12-year-old point-and-shoot camera where I took a bunch of photos of the pits and then we stitched them together into these DEMs. And you can actually see that the cone shape is an okay assumption. You can see the 2 pits on the right-hand side look much more cone-shaped than the ones on the left-hand side. But the one on the bottom left that we labeled D22, you can see it's kind of halfway in between a bowl and a cone. So we're feeling pretty good about using this assumption of them being a cone. Although, you know, if they're a little bit more bowl-shaped, it definitely introduces some error into our measurements, but we can at least understand what that error might look like because we know what the other shapes would be. So in order to test the assumption that the pit diameter relates to pit depth, you have to go out and measure them, which is what these hilarious pictures of me are doing. So we measured the location so we could put them all into ArcGIS after the fact. We measured their diameter. A lot of times these pits are pretty elliptical because if the crack that they're forming in has opened up quite a bit, that pit can sometimes get really long and not as wide. So they can sometimes be kind of elliptical. So we measure them in two different directions. And then we also measure their depth. And you probably can't see it, but that's me using a laser rangefinder to try and estimate the depth. Which is tricky, right? You can see all this vegetation, which causes big problems. And also, I don't have a good picture of it in this presentation, but in many cases, these pits are kind of bottomless. And so as a human in the field, you have to be really careful to not fall into the pit of despair. So you really want to just make sure that you don't, you always want safety to come first. So the laser rangefinder was great because getting into a hole that doesn't have a bottom to try and measure how deep it is really complicated. So along the lines of trying to understand the relationship between pit diameter and pit depth, we decided to plot it up. And this is essentially the same plot in two ways. The plot on the left is showing you each of our data points, and the plot on the right is just simplifying those into their trend lines, right? So kind of the average trend. And I think the first thing that really pops out, the first thing that you really notice is that all the blue dots, which are field areas 1 and 3, those are the grassy ones with all the vegetation that I showed you here, right? This is field sites 1 and 3 terrain. Those are represented in blue, and then study area 2, which is that really sandy material, is represented in all these yellow circles. And so you can see the yellow and the blue fall out from one another, which is showing you that in general, you have larger pits forming, larger, deeper pits forming in this sort of grass, sorry, I'm not saying that right. Your pits are deeper in the grassy areas, and they're shallower in the sandy areas. And we think a lot of this has to do with the fact that you actually have all that grass and all that vegetation. This stuff is really woody. If you've ever been to Iceland, it's these really thick shrubs, but they're really low and they're really woody. They're kind of hard to walk on. They make these great big sort of mounds. We think that's really propping up the regolith. So you can actually get steeper and steeper and steeper pits because rather than relying on the angle of repose of the regolith that we have here, or the soil, you have all those plants kind of holding that in place. And so this relationship isn't holding up quite as well because the material is not as loose. You're not relying on the properties of the material, you're relying on the vegetation, which of course we don't have vegetation on Enceladus, so that makes it a little bit harder. But generally speaking, there is a pretty good relationship that we're seeing here, but we wanted to go one step further and test it. And so we did this using a ground penetrating radar. And essentially that allows you to sort of use electromagnetic radiation to essentially get a snapshot of what's going on in the subsurface. So we did this a couple of times using 2 different antennae. I'm only going to show you the results from one antenna, which is this 400 megahertz antenna, which is that little orange box that you can see. And you essentially drag it along the surface. And it sends energy into the subsurface, and that reflects back at you into this control unit, which is that blue box that my colleague Jennifer Witten is carrying, and you essentially can image what's going on there. And I'll show you a radargram. So this is essentially the kind of picture we're looking at, and we were looking for what we hoped would be the interface between all that soil and a bedrock layer. We think we see it, which is indicated by this dotted red line here. The challenge is that our 400 megahertz antenna has a pretty shallow penetration depth. As you can see, we only got down about 2.5 meters. But we wanted to test how accurate that was by doing some secondary measurements. These are always really important when you go into the field. It's always really important to consider what kinds of weather conditions might you experience that could interfere with the measurements you want to take. If you're running a ground penetrating radar system, you know that really wet things do not play nicely with ground penetrating radar because the radar signal will reflect right off the water or wet thing that you're trying to measure through. Because Iceland can be a really wet place, we came prepared with these tiling probes, which are essentially a steel rod you hammer into the ground. And when you can't hammer the steel rod into the ground anymore, you make the assumption that you've hit the bedrock. And we would make multiple measurements in each location. And we did this because we never knew how wet the soil was going to be. We didn't know how high the water table was going to be. And so we wanted to make a secondary measurement. When you spend resources to go into the field, you always want to have a backup plan. So this is also my colleague Jennifer Witten hammering the tiling probe into the ground. If we only ever got a few inches down, we knew we hit a rock. So we always pulled it back out and did it again. So we did multiple measurements. And what's really interesting is if you actually look at the tiling probe measurements, which are on the right-hand side of this image, just those lines going down, they actually do a pretty good job of matching up with where we think we found the bedrock interface. So essentially what we found was that not only is there a relationship between the depth and the diameter of these pits, but we can also use the pit depth to register with the depth of the regolith. And we actually think that this relationship holds up best when we're talking about a loose unconsolidated material. So you're looking at similar data to what I showed you, but it's on a grander scheme looking at other pit chain measurements across the solar system. And to walk you through it, these green dots up here are all measurements of pit depth and diameter made on Mars. These orange ones are some preliminary data that I did on Enceladus, and I'm very close to making this a little bit of a better plot with some updated measurements. These purple boxes represent some small bodies. So there's some pit chains on the small body series, which are represented by this purple box. Gaspra and Phobos. Gaspra is a moon of Jupiter, and Phobos is a moon of Mars. They are represented in these purple boxes. Eros and Ida are represented by this purple star. So we've got a lot of, like I said, you already know, there's a lot of places in the solar system that have pit chains, but they're all kind of following along this general trend until we get here to Iceland, which of course they're all much smaller in Iceland, which we would have expected. But you can really see that these yellow data points, which represent our pits that form an unconsolidated material, that really sandy material, fit along this trend line much better than the pit chains, which are these blue dots here, that are formed in those really heavy vegetated areas where the vegetation is really kind of getting in the way of us seeing how that material is really behaving in real life. And that really bears out in this plot because you can really see that the overall trend of that blue line is really very different than what's going on with these yellow data points. So this is just another image to try and show or prove that the material really matters. So site 1 is one, obviously it's heavily vegetated, and you can really see all these shrubs really holding up the walls, and you can really see these things are much steeper than in this really sandy area. The sandy area is not, you know, without its own vegetation, but you can really see that you're much more at the mercy of the actual material itself rather than the vegetation. It was a really interesting time to actually be looking at these areas because they were in the process of trying to preserve their soils in this area by planting, I believe it's Canadian lupin. So a lot of these really bright green areas are actually lupin that's been planted there to try and keep that sand and that soil in place as part of a conservation effort. So we were actually able to see this in 2 different years, and we have some colleagues who traveled to Iceland about 10 years ago, and we've seen pictures from their field work, and this lupin has really grown. So it was really great to be able to have their data set at a different moment from the data that we collected. So we think it's really important that we maintain the assumption that the physical properties of this material are loose and unconsolidated. Of course, we haven't gone to Enceladus and tested this, right? We haven't put a robot on the surface of Enceladus, so we don't really know. But before I run out of time, I want to show you, now that I've shown you or tried to prove to you that using the fieldwork in Iceland gives us the confidence to move forward and employ this tool on Enceladus. I want to show you what those results look like. So we know it works in Iceland if the material is loose and unconsolidated. So we're going to move ahead with that assumption without having sent a robot there to go find that out for us. But we feel confident that we can actually move ahead and come up with a meaningful map of the depth of the regolith across the surface. So without boring you with the details of how that works, essentially we measure the diameter of the pit, the length of the shadow. We get some information out of the images in terms of what angle the sun is coming and hitting the surface at, and we come up with something that looks like this. So what you're looking at is each individual data point is an individual pit that we measured. Now, we didn't measure every single pit because that's hard and that's time consuming, but because we're dealing with really small features at the resolution of the images that we have, we were really conservative about how we made selections about what we were going to measure. So when you look at this map, you can't assume that the absence of a pit is the absence of a pit chain, if that makes sense. So right up here, we do have quite a lot of pit chains, but there were no individual pits that fit the really strict criteria that we set out for ourselves. And we set a really strict criteria because we wanted our measurements to be really robust and we wanted to be really confident about those measurements. So red dots mean we measured a pit, and at that pit, we measured or inferred that the depth of the regolith is really very deep, on the order of 1 kilometer or more. Places where you see blue or greenish dots, that's a place where we measured a pit and the regolith was much shallower, on the order of 100 or hundreds of meters of material. And you can see in this histogram that generally speaking, 1 kilometer deep or more is pretty unusual. Our overall average regolith depth is in the hundreds of meters. And what's really interesting about the distribution of our pits is if you actually compare the distribution of the pits we measured and the distribution of the pit chains that we mapped, which I showed you at the beginning of the presentation, and yeah, it's right here. So I'm going to skip over to the map because while this is really useful, what's more useful is to actually compare the map of where pit chains exist, right? Because I already said there's a selection bias when you look at this map, and I don't want you to think about the selection bias. I want you to know where we have pit chains. So this is a map of pit chains. All the green, I should say all the teal or the cyan color, those are all pit chains. The green color are features that we're calling candidate pit chains. There's features that are really close proximity to a pit chain but don't have all the exact morphological characteristics because of image resolution. So we don't want to classify them as a pit chain because we can't technically prove it. On the right-hand side are computer models. These are models that are saying, okay, we have particles coming out of the South Pole. Where do they fall on the surface? So the two different models are represented by the two different eruption styles. The one on the top, right, is a jet eruption style. This essentially says the tiger stripes on the South Pole or pole of Enceladus, all those blue cracks that I showed you kind of at the beginning. All of those particles are coming out of individual jets, kind of coming out of the surface like this. And in that eruption style, you would get this distribution. So all the white, bright white stuff is sort of representing where you would get material falling. The model on the bottom is if the plumes are erupting as curtains, which essentially means rather than kind of coming out like this, it's coming out like this. So a big sheet of material flying out of the South Pole. And the distribution of material falling onto the surface looks a little bit more like this. Now, we're not at the point yet where we're ready to claim one or the other model as being correct. But what I would point out is we think we have a lot of candidate pit chains up in the North Polar area. And you can't do that robustly using the curtain eruption model. It's much more likely that it's the jet model. So don't quote me on this yet, but you can quote me on this soon. And so we're continuing to map out the distribution of pit chains. But fundamentally what we've done is we've been able to say, okay, here are all the locations where we can confidently measure the regolith depth, and how does that compare to where we would expect material on the surface, and how much would we expect to see? And on this side of Enceladus, it actually seems to fit really nicely. You would expect to have more material falling closer to the South Pole because it's closer to where it's erupting. So you would expect more material there. And so this actually goes from deeper material to shallower material as you move further away from the South Pole, which really fits what we think. This part of Enceladus, it doesn't fit quite as well. We're still trying to work that all out. But fundamentally, what this is going to be able to do is give us an opportunity to make a first guess, a first order estimate of how long there's been plume activity. So I'm going to take you through a brief thought experiment just as an example of how we would do this. So we're going to say an average regolith depth of about 400 meters. I'm picking that number because it's not exactly right at the top of our histogram here, but our histogram doesn't have a perfect normal distribution. So I'm picking a rough average that I'm going to call 400 meters. This is the mean of the data set approximately. So if you look at this particular model, this is the jet eruption model. If you use a deposition rate of 1 millimeter per year, which is this bright white region down at the South Pole, that's the most accumulation they think you could get, the highest accumulation rate, which is about 1 millimeter per year. So in order to get 400 meters of material, it would take about 400,000 years to accumulate that much material on the South Pole, which isn't very much time. If you use the slowest rate of accumulation, 10 to the negative 5 millimeters per year, it would take 4 billion years in order to accumulate 400 meters of material, which is a little bit less than the age of the solar system. So not impossible, but probably unlikely. So we're probably somewhere in the middle there. So if we take a rate of 10 to the negative 3 millimeters per year, we're looking at 40 million years, which is geologically very easy to imagine. So what's really interesting about these numbers is that these rates, 1 millimeter per year, assume that the density of the particle coming out of the South Pole is that of liquid water, which it's not, which means that these deposition rates are actually much greater than what they've presented in their models, which is really exciting for us because it means that, you know, even if we use a really slow deposition rate, these deposition rates are really conservative, which is really interesting, I think, because what we're seeing here is that if you just do back of the envelope calculation, our rough estimate is that it's going to take somewhere around 4 billion years or less in order to deposit this material. And that's a really good amount of time to have a habitable environment existing on a planetary body. Now, I mean, that assumes that plume activity also relates to the existence of an ocean, which we think is a pretty good assumption to make. Although I'm sure we could come up with situations where that doesn't work out as well. But the point being that we're really close to being able to use the material that we have on the surface of Enceladus to infer something about what's going on in the subsurface and give us a better sense of what kind of timeline we're looking at for maintaining a habitable environment on Enceladus. So I just want to leave up this summary. I think what I'm really excited about this project is that we have this tool that we can use just by looking at individual images of the surface of Enceladus. This is exciting because we also have a place in Iceland where we can go and actually look at these features in person. And we can ask questions that we couldn't ask at Enceladus and actually really use those two things in concert to be able to be much more precise and much more confident in how we develop this tool. Because what's cool is that while we can do all of this for Enceladus, we can take this tool and extrapolate to other parts of the solar system where we see pit chains and try and say something else about, you know, how deep is the material there, what is the source of that material, and can it tell us anything about what's going on in its subsurface, even if we don't think it would have a global liquid ocean. So with that, I'd really like to hear what you all think and see if you all have any questions about Enceladus or ocean worlds or anything that has come to mind.
Thanks, Emily. So we've got a ton of questions here, and I'm going to try and kind of group them together as best I can. And certainly if more things come up, folks who are listening, you know, you can go ahead and put them in the chat window, and we can keep the discussion going here. So the one thing I want to start off with is, how do you find and choose different field sites?
Yeah, that's a really interesting question, because I got into the field of planetary science specifically because of my love of icy moons. So moons are the gas giants, moons in the outer solar system. And so as I got involved in the field, I had the realization that fieldwork was maybe not going to be a tool in my tool belt, because there's just so few places on Earth where there's relevant field sites. The ice in the outer solar system is too darn cold to be the same kind of ice that we see on these icy bodies. I mean, we actually use things like basalt as a similar material properties to the ice that we see on places like Enceladus, because it's so cold, it acts so brittly that it really faults and fractures the same way basalt does. So we think about materials. Where do we have materials that have similar material properties? Iceland's perfect for that, because as I said, basalt has really similar properties in terms of how brittle it is to the kind of ice that we're seeing on Enceladus. So you want to talk about material properties. You also talk about, features, right? What are you trying to do? What are you trying to study? So in this case, we got really lucky that we had similar structures in Iceland to what we were seeing on Enceladus. So sometimes you pay more attention to the kind of structure, right? Like if you study impact craters, you might go to meteor crater, or you might go study the Chicxulub impact with some kind of fancy technology because it's under the water. But the point being, you always have to understand that your field site's never going to be a perfect analog. So you always have to focus in on the thing that's the most important question to answer by going into the field. And so that kind of narrows down whether or not it's the material that matters the most or the landform that matters the most. Other than that, I don't have any really great advice, other than part of this was motivated by the fact that I started studying pitch chains about 12 years ago, and I always wanted to go see them in Iceland, and I never had a really good reason to go do it. And I finally came up with this hypothesis a couple years ago. I was like, wait a minute, we can actually go ground truth this idea. And so that's what got us to go ahead. And so that's really what it comes down to is, as much as geologists love being out in the field, it takes a lot of energy and effort to find the funding to actually support that. And so you really want to make sure that you have a really good testable hypothesis that you can bring out into the field.
There's actually been a lot of questions about the pits themselves, and in a couple of different areas. And one is, how do you differentiate impact, on a moon like this, how do you differentiate impact craters from the actual pits? And then with material being deposited, from what it's erupting, how, are the pits obscured? And then, of course, the pits that you're studying in Iceland are subject to, weathering. So how does that alter them, and how do you begin to make those comparisons?
Sure. So there's a couple things that help us understand the difference between a pit and an impact crater. The first is that an impact crater typically has a raised rim, and you don't see that on a pit chain. One way to show it, on Enceladus, things are all messed up because it's hot and things are relaxing and it's pretty much snowing. This impact structure here is called a catene. This is on Ganymede or Callisto, one of the moons of Jupiter, and this is essentially an impactor that came in, broke up into little bits, and created this crater chain. But it's an impact crater chain, and I don't know if you can see it with your eye, because it's a little bit small probably on your screen, but an impact crater has these raised rims, and it's very clear. And then the other thing is the assemblage, right? And single impact crater doesn't look like individual chains of pits all linked up the way you do on Enceladus. So you can see on Enceladus, these are all impact craters sitting underneath this parallel series of fractures that have this mottled appearance that indicates that they are pit chains. And what was the next question? It had to do with pit material, erosion, and vegetation?
Well, so, on Enceladus, there's material being deposited on top, and how might that obscure the the pits there versus on Earth where we have weathering processes that can alter the shape of the pits?
So I'm going to give you my impression, but I haven't been able to prove it yet. So I mentioned that pit chains are young features. They are some of the youngest features on the surface of Enceladus. They lay on top of all the craters. They lay on top of all the other tectonic features that you see. Probably at the scale of your screen, this isn't really easy to see, but all the small things indicated by black arrows are pit chains, and if you squint, and trust me, all those features lay on top of everything. So while the material coming down onto the surface of Enceladus will cover some of those up, you have to remember we're talking about millimeters of material per year on features that are kilometer scale. So at the resolution that we have, you know, if these pit chains are as young as we think they are, they're probably still forming in many cases. And if that's the case, you know, we're talking about years or millimeters of material falling down onto kilometer scale things. So these pit chains aren't 40 million years. They are dissecting 40 million years worth of material. And as a result of that, you're not subject to covering that all up. We're getting to see it right now. However, that's me trying to create a logical flow through the problem. And I can't prove it. I can only tell you that that's what I think because I'm confident in the observations that I've made. But erosion happens everywhere, even if you don't have flowing water on the surface and wind blowing, right? A place like Enceladus has erosion because material is still falling down onto the surface, right? That is a kind of erosion, even though it's not pulling down pit chains. It's, you know, constructing material on top of them. So it's a really good question, and it's something that we have to think really hard about. And that's part of why we do these really basic analyses of like, is everything on top of pit chains or are pit chains on top of everything else, right? That's a basic question, but it's really important for us to know that they're young features because otherwise we wouldn't be able to make these kinds of conclusions.
All right, so I'm going to go to probably the most common or the favorite question here, and it's kind of complicated, so we can talk about it in pieces. But
okay.
People are really interested in ocean planets, ocean moons, you know, in our solar system.
Good, you should be, because they're awesome.
And, you know, so the first part for Enceladus is, how do we know it's water? And even some of the other ones, how do we know that it's water and not some other material? And then the second part is, what do we know about, you know, the conditions of the ocean beneath that ice cap and, you know, like the chemistry of it and the conditions, and what's the possibility of life there? And if there is life, what might it look like?
Whew, wow, you really wrapped those all up into one.
Yeah, that's a lot.
Yeah. Okay, so I'm gonna try and answer the first two with one answer. We know that it's water, and we know its other little composition, right? We know that there's some carbon dioxide, and we know that there's some other yummy organic-y bits that microbes might be interested in. Because we actually took the Cassini mission, and we flew it through Enceladus's plume, which means Cassini literally tasted Enceladus's ocean water, right? So we literally flew a spectrometer through Enceladus's plume. That's part of how we know it's a salty, not organic rich, but definitely has some organics in there, primarily water. That's part of how we know the composition. And that's part of how we know the oceans are water. The other way that we know is the first ocean world for us to sort of identify was Jupiter's moon Europa. And we actually know that there's a liquid in the subsurface because Europa has an induced magnetic field. So magnetic field around Jupiter is really intense, and there's actually this induced magnetic field around Europa, which is the result of there being a salty water ocean, because of course you can not transmit current through plain water. You need to have that salt in there to make it conducting. So we actually have multiple measurements we have 2 measurements from 2 different ocean worlds, but they're 2 different kinds of measurements. And, you know, if it's not H2O, what would it be? So there's kind of that basic logic-y question. Plus, we know the overall density of these bodies, right? And the overall density of these bodies are, I think Enceladus is like 1.1 and Europa is like 1.3 or 1.4. And if these things have rocky cores, can't really be much else other than liquid water before that density just doesn't work anymore. So then the next question was about habitability and whether or not these things are habitable. So this goes back to some of the early slides. You need to have liquid water, we think. You need to have energy, heat source, something like that. But energy also comes up with, you got to have the right chemistry, right? You got to have something for these things to live on. It doesn't have to be oxygen and photosynthesis, right? But it has to be something. And so that's why going and flying through Enceladus's plume was so revolutionary, because it was a little bit of a risk. It wasn't something that Cassini did at the beginning of its mission, because they didn't know they were going to find a plume there. And to fly a billion-dollar robot, multi-billion-dollar robot through an uncharacterized plume of gas and vapor and particles and all that kind of stuff is a huge risk to take. So, you know, we know what the composition of Enceladus's ocean at least partially looks like because of what they've measured in the plume in terms of chemical components. And so we know there's some yummy organics in there. We know that there's enough energy in Enceladus to keep that ocean liquid. Enceladus, like I said earlier, it's the size of Washington State. That should have frozen a long time ago. It should be a floating ice cube, but it's not. It's got a big layer of liquid. So there's a heat source being generated between this push and pull between Saturn and Enceladus. And actually Saturn's pull on Enceladus, which partially keeps it in orbit, also is what keeps Enceladus warm inside and what keeps that liquid water ocean liquid. So we have the energy, we have the chemistry, we have the liquid water. But what kind of life is that going to look like? It's definitely going to be microbial. If you've ever watched Europa Report, I don't think we're going to find that at Europa. I don't think anybody's expecting us to find large creatures, right? I don't think there's going to be any trilobites. I don't think there's going to be any ammonites. I don't think there's going to be any of that kind of stuff. I think it's going to be largely microbial. And that's the kind of life that the astrobiology community is really developing their technologies to try and detect.
So is it more like deep ocean around, say, black smokers kind of chemistry and stuff?
I think that's the idea. Although, of course, when the black smokers and the life around the hydrothermal vents was discovered, that was an enormous surprise. I don't think anybody expected to find the huge, what are they, tube worms or something?
Right,
like,
yeah.
Nobody expected to find something that big and dynamic around those things. They expected it to be too hot and inhospitable to find the thriving communities of ocean life that they found around those places. So, you know, I think there are hypotheses to suggest that there is hydrothermal activity at Europa and at Enceladus at the ocean floor, at the rock ocean interface, not the ice ocean interface. So at the rock ocean interface, they think that's a possibility. And part of that is because both of those moons have enough of an interplay with their parent planet that they're generating enough heat to keep those liquid water oceans liquid, but also to drive geologic activity. Right? The ocean has much less to do with Enceladus's tiger stripes. And much more to do with this heat constantly being released from Enceladus. You know, Earth is still cooling off too, and that drives all that geologic activity that we have at our surface. And it's the same thing with Europa and Enceladus. They're much too small. They should have cooled off an awful long time ago. So I think the idea that there's hydrothermal vents at that ocean rock interface is really intriguing, and some of the chemical compounds, which I don't know off the top of my head, that they found in Enceladus's plumes suggest that it's ongoing on Enceladus.
Okay. A couple people have asked, besides Europa and Enceladus, how many other ocean worlds are there?
I love it. I actually don't know the number, but we can count. So if you count, can we skip Earth and Mars?
Yeah, we can skip those.
Okay. Because really, if there's no ice, it's not worth it. So Europa, Jupiter's moon Ganymede, and Ganymede might be cool because it could be like ice, ocean, weird phase of ice, more ocean. It could be kind of an onion skin. We don't know. So Europa, Ganymede. Callisto, another moon of Jupiter, has a really thick ice shell and then probably a thin liquid layer. And then Enceladus is definitely an ocean world. Saturn's moon Titan is probably an ocean world. You could throw in maybe Dione, another moon of Saturn. I want to give that a half because that's jury's still out on that one. Then Uranus's moons, jury's out on those two. And then Neptune's largest moon, Triton, is almost certainly an ocean world. And then Pluto is probably an ocean world. Its moon, Charon, not sure. And then I need to double back and go to Ceres, which is also a dwarf planet that resides in the ocean, in the asteroid belt, is also probably an ocean world, or at least a relic ocean world. I lost count, but we're at least at like 10-ish. Especially when you consider all the maybes. So there's a lot, and this isn't really a term. This isn't a class of bodies that we've talked about for very long. This is really coming out of the Cassini mission. I mean, the Galileo mission showed us that Europa was an ocean world, but we didn't really understand that was going to become a class of bodies.
Mm. So I know we're getting close to time here, but I'm just going to ask a couple more.
Please, carry on. This is the best part.
So do we know why it's only erupting from the southern pole?
Shoot. If they had a Nobel Prize in planetary science, I feel like it might be on the list if somebody solves it. The short answer, the easy answer is it's probably because it's thinner there. The ice shell is thinner there, and therefore the ice shell is weaker, and therefore it's easier to crack, and therefore it's easier to use that as the place in which all this heat gets expended. But is it active there because it's thinner, or is it thinner there because it's active? And so Enceladus is full of these kinds of dichotomies. This slide I have up right now is a really great example. You've got the crater terrains, which sit on the Saturnian and anti-Saturnian hemispheres, and you have these tectonized terrains that sit on the leading and trailing hemispheres. It's like a tennis ball that just got stuck together. Enceladus is weird like that. This is a great question, and I don't have a great answer to it because all of it requires that there be some initial heterogeneity that made it easier to fracture the South Pole and allow that to be the place where the geologic activity happened. True polar wander, giant impact. The answer is still not great because you always still have to seed that initial focus of that energy, and what that should be isn't clear. I'm working on a group with folks who are trying to look for geologic evidence of a giant impact. Does it exist? We don't know, but we're going to go look for it because if it happened, it'd be really convenient. Not to mention, Enceladus doesn't have a giant impact basin. Mimas has a giant impact basin. Dione has multiple giant impact basins. All the moons have giant impact basins except for Enceladus. So it's not impossible. Statistically, it should have one. Cratering statistics are completely a mystery to me, but the statistics tell you that you should have at least one giant impact basin, and Enceladus doesn't have one. And if it had one, it should be about the size of the South Polar terrain. It's a little convenient, I grant you, but it's a great question that I can't answer because it's the question that everybody's working on and everybody has great solutions to, but none of them are the solution, I don't think, yet.
Well, that's why we do research, right? So for the ocean planets, tectonic features, as in plates and pit chains? Are they common? Are they common features?
So I'm not entirely sure I totally understand the question, but the first thing I want to say is when it comes to tectonic features, Earth is the only place where tectonic features are driven by plate tectonics. When we talk about tectonic features anywhere else in the solar system, we're talking about we're talking about faults and fractures that are forming due to stress, like all faults and fractures do. But the source of that stress is not the movement of tectonic plates. Earth is broken up into multiple plates. All the other planets in the solar system, all the other places with hard surfaces in the solar system, you have to essentially think of as single plates. And so those stresses don't come from the movement of plates. The stresses that create the faults and fractures on these bodies come from mostly the constant force that's being exerted on the icy shells of these moons from their parent planets. So moving from there, tectonic structures you find almost everywhere. Whether it be the result of stress from an impact or from the tugging of a parent planet, from some kind of volcanism. Tectonics exist on almost all bodies with a surface. Not all, there's always exceptions, but they're pretty common. And pit chains are a little bit less common, but if you essentially think about all the different kinds of pit chains that you can have, we have right here on this slide alone, we have 8 different ways in which you can create a pit chain. We've got volcanic ones, we've got lava tubes collapsing, secondary impact structures, right? Material that flies out of an impact crater as it's forming can actually create these linear chains of pits of material just being ejected out of the crater, and it lands all down in this single trajectory and it looks like a pit chain. So tectonic pit chains are less common, but you still find them on, I don't know where that slide is. I would say of the ones in this image, the ones on Mars, Earth, Venus, Eros, Phobos, Vesta, and Ida, those are all probably tectonic. So it's not uncommon, but it's not as common as, let's say, cratering, which is the most pervasive geologic process across the solar system.
All right, so I'm going to ask the last question. I'm going to hope that it kind of brings together some things that people have been asking, but where do we go from here? So what kind of technology, what kind of missions might we employ to answer some of these outstanding questions?
It's a really good question, and some of these are going to be really great answers because I can tell you this is happening, and some of these are a little bit more aspirational because they're things that are being discussed. And then there's a couple in between. So the next thing that's happening is the Europa Clipper mission is a large space robot that's going to go back and investigate Europa. When I first started in planetary science a few years ago, my very first planetary science conference I ever went to, somebody was handing out buttons that said Europa or bust. People have been talking about going back to Europa since before the Galileo mission took its swan song into Jupiter. So, everybody knew how special Europa was. Everybody's been trying to get back there since they realized how special it was with a mission that was really dedicated. So the Europa Clipper mission should be launching somewhere between 2023 or 4 or sometime soon after. It's a multiple flyby mission. The radiation environment at Europa is a beast, and doing what's called rad hard, radiation protected hardware, is really heavy because you got to wrap it all in lead. So what they're doing is they're actually doing these really elongated orbits around Jupiter where they kind of fly by Europa, take a bunch of data, slingshot out around Jupiter where they can kind of let the radiation cool off, and then come back in and and fly by really closely to Europa again. I think the initial mission is something like 30 or 40 flybys. And from there, they're essentially going to do global global imaging, high resolution imaging. They're going to be looking at the ocean. They're going to be looking at the ice shell. They're actually carrying a radar instrument, an ice penetrating radar instrument. So hopefully they can actually identify whether or not there's lenses of water or brine in the ice shell, and whether or not they can actually measure how thick the ice shell is. Lots of really cool fundamental science. So we're going to characterize ice shells, we're going to characterize oceans, and we're going to characterize the surface, because there's a lot of outstanding questions on Europa because of the data. So that Europa Clipper mission, totally happening. After the Europa Clipper mission, there's a little bit of there's a lot of discussion that's going on about the Europa lander. Now, the initial concept was that 2 years after the Europa Clipper mission launched, you would launch the Europa lander. So Europa Clipper would arrive 2 years early, do all the reconnaissance. So by the time the Europa lander showed up, you would have enough data to know exactly where to put that lander down. And that lander would have a seismometer, it would have a drill, and it would really characterize the surface and characterize the surface environment for us, and give us a really great sense of what's going on. The Europa lander is still a concept, but what's really exciting about it is it's really driven an enormous amount of innovation when it comes to penetrating through ice shells to try and tap into oceans. Part of the trick is that Europa's ice shell could be 5 or 25 kilometers thick. Getting an instrument package that far down is really challenging. But NASA is committed to developing that technology, and there's an enormous number of folks working on developing those technologies. But there's other smaller missions, right? The Europa Clipper mission is a huge flagship class mission. Flagship means, it's a couple $1 billion. It's the biggest class of missions that NASA flies. There are multiple smaller missions, right? The New Horizons mission, which flew by Pluto, was a medium-sized mission for NASA called New Frontiers mission. So there's some New Frontiers mission concepts to go back to Enceladus, and a couple other icy moons to try and learn some more. And then right now, there is a competition for the Discovery class missions, which is the small class missions. There's 4 finalists who are currently in competition. I'm on one of those teams, and one of those teams is actually proposing to fly by Neptune's moon Triton. Not to be confused with Saturn's moon Titan. I swear they didn't keep us in mind when they did that. So it's a flyby. This is very much like the New Horizons mission, where it just flew by Pluto and it just kept going. So the concept is to fly by Triton. Triton has probably one of the younger surfaces in the solar system, very few craters. It was seen by Voyager 2 back in the late 80s, a while ago. And, detected plume activity. We don't know if that's plume activity tapping into an ocean, or if it's sort of a sublimation effect. But we're hoping to get to Triton, right? There's 4 mission concepts that are being competed. They're going to select 1 or 2 missions. I can't tell you what's going to happen with that because I don't know. If I knew, I'd tell you. But, it's flying a magnetometer because we think that Triton has an ocean underneath its ice shell. So because habitability is such an important part of NASA's mission, ocean worlds are becoming a much more important focus for NASA missions, NASA research funding, and NASA programs. So I think, if you're somebody who's interested in ocean worlds and studying ocean worlds, this is a great time to get into to be involved, because it's really a direction that NASA's really committed to going.
All right. Well, thank you. Thank you. Great talk. For attendees, I apologize if I didn't quite get to all of your questions. There were so many. I was trying to condense them all so we cover as much as possible. And I hope you enjoyed this, and thanks for attending. And again, thank you, Emily. It was great.
Hey, thanks so much for having me. I had a really good time.